Hello and welcome to this clip on fuel cells. We'll start by looking at the difference between primary and secondary cells, and we'll look at fuel cells themselves and some of the electrochemical principles behind them. Before we go on to the detailed electrochemistry which happens in acid and alkaline hydrogen fuel cells. It's assumed throughout the clip that you're already comfortable with basic redox chemistry and have already had a look at electrochemistry beforehand. If you haven't, it might be worth going and making sure you've done that before you continue. So you may well have come across something like this in textbooks prior to your studies at A-level. It's a simple electrolysis, but the difference between this and some of the other cells you might have looked at in your work at A-level are that the source of the electrons comes from the battery. The battery is external to the redox system of interest. In the cells that we're going to look at in this clip, the cells themselves are the actual redox system, just like we've looked at in other areas of electrochemistry. So what we're going to do is actually look at some electrochemical cells where a flow of electrons is actually produced from a redox reaction, pretty much the same way in which you've looked at other cells and electrochemical systems so far. But this time what we're looking to do is try and find electrochemical cells that produce a sufficient flow of electrons to actually produce power, enough current to run a device like such as a phone or a light bulb, for example, or maybe even electric motors. So many common devices use electrochemical cells to power them. You'll no doubt have seen batteries, and you may well have a phone that has a battery. Most people do, I suppose. The device I made this video clip on is charging at the moment while I'm making this clip, so it obviously has a battery of its own as well. So any battery, whether it's rechargeable or not, is called a storage cell, because it means that there's chemical energy stored up in the battery to become electrical energy when the battery is connected to a circuit. And the conversion from chemical energy to electrical energy takes place via a redox reaction, and the force that pushes the electrons along is called the electromotive force. So storage cells can be classified as either primary or secondary. And the difference between these two types of cells is that primary cells can only be used once, whereas secondary cells can be recharged. So you'll probably charge your phone up. Your phone will have a secondary cell. Your tablet might have a secondary cell. My bike lights, I use secondary cells. You can buy rechargeable batteries which are secondary cells. So there's a picture of my bike light batteries being charged up. So each of these has a slightly different electrochemical system. So for the alkaline style batteries that you can see in the photo on the left, you may even just be able to make out alkaline in some of the printing on the batteries, but the vast majority of primary cells these days that we buy in the shops are alkaline based. And it's this particular redox system that they use. And if you already had a look at how we decide using electropotentials, whether it's an oxidation or reduction out of two half cells, you'll know already that the manganese dioxide half cell has a more positive electropotential, so it remains as a reduction, but the zinc oxide half cell is reversed because it's got a less positive electropotential. And by cancelling the common species, H2O, OH- and the electrons, you can come up with this overall equation for the redox reaction. And it would obviously be plus 1.43 volts. So secondary cells are typically nickel-cadmium based, or nickel metal hydride like the batteries in the photograph, or maybe lithium ion based, such as the ones you might find in a phone or a tablet or a more modern piece of equipment that charges up. So you'll no doubt recognise these types of chargers. When they're attached to a phone or a tablet, what they'll do is charge up the lithium ion battery that's inside the device. And it's obviously really important to use the right type of charger for the device, so always use the manufacturer's recommended charger. There have been instances where some devices have caught fire while charging because the lithium ion battery has overheated. So it's a possible disadvantage of lithium-ion batteries. There have been some reported cases of devices actually setting alight because of this problem. So it's very important that you use the right charger for the battery in your phone or your device. This is my other bike light secondary cell being charged. You can see from the cable that it's got a built-in cell this time. So what's happening here is it's being plugged into the wall, just like your phone's cell might be plugged into the wall. Okay, so I better be moving on with this now. Let's have a look at fuel cells. So the hydrogen-oxygen fuel cell is an example of a fuel cell. Fuel cells basically use the energy released when any fuel reacts with oxygen. So there's a variety of different types. The most common type is the hydrogen-oxygen fuel cell, which is currently being developed for use in cars as a possible future alternative to fossil fuels such as petrol or diesel. As you'd expect, this is an electrochemical system, and it's got its own set of redox equations, a reduction equation and an oxidation equation. So this type of fuel cell can have either an alkaline or an acidic electrolyte. The diagram on the top right of the screen actually shows an alkaline electrolyte. It doesn't really matter which type of electrolyte you've got, you end up having the same overall reaction. However, the individual reductions and oxidation half equations are slightly different to each other. So we need to be aware of these and have a look at these next. So let's look at the alkaline electrolyte hydrogen fuel cell first. I've drawn a very simplified diagram of it, and you have the two half equations written as reductions to start off with their equivalent electrode potentials. And as you'd guess, due to the electrode potential of one of them being less positive than that of the other, the one with the less positive electrode potential is reversed. So you get an oxidation and a reduction. So this gives us the overall cell reaction, and the cell potential is 1.23 volts. Let's now have a look at the acid version, the acid electrolyte. This too is composed of two half cells. They're written as they would be written in the electrochemical series, both as reductions. So let's take it from first principles and work out from electrode potentials which one is reversed. When looking at the data, it's not difficult to work out which one will be reversed. So the top one will be the oxidation. So that's our two half equations, the correct way round. And cancelling common species and electrons on both sides, that's our overall equation, exactly the same as with the alkaline version. And again we get 1.23 volts. So very similar, but there's subtle differences as well. The subtle differences between them are worth memorising. It's worth making sure that you know these because it's highly likely they'll come up in exams. We also need to quickly look at the advantages and disadvantages of using hydrogen fuel cells. Where they don't solve all the problems that we're facing, they do have a few problems of their own. So one issue with hydrogen at the moment is in order for it to support an infrastructure where hydrogen-powered cars could go and fill up with hydrogen, as the diagram in the top left-hand corner suggests, is to actually find a way to store it, because it's actually highly explosive, as you probably know. You've obviously done the hydrogen test in school, where you take a lighted splint, hold it at the top of a test tube where there's hydrogen being produced, and you get a popping sound like this. So obviously, that's a very small amount of hydrogen. If you imagine a hydrogen station, if there's a spark of any kind, even from a mobile phone, I say don't use mobile phones in petrol stations, so if for some reason there was an ignition source, the whole thing could explode suddenly and create a very large fire risk. So at the moment what we're looking at is different ways of adsorbing hydrogen molecules, either onto the surface of a material or absorbing them within a solid lattice as hydrides. Now Now this requires either adsorbers or absorbers, indicated by the green or the blue atoms in the diagram, simplified diagram at the bottom of the screen. These themselves have to have enough durability and reliability to be able to hold the hydrogen in place so it doesn't become a gas. If it becomes a gas and can be released inadvertently in an uncontrolled way, it's then going to be an explosion risk. So this is something that has to be overcome if we're going to scale up the use of hydrogen as a viable fuel to compete, or will take over even, from fossil fuels such as petrol and diesel. So let's look at the advantages to start off with. So obviously they have quite a lot going for them, and a lot of these advantages are quite big reasons to start looking at switching over to a hydrogen-based economy as opposed to a petrol or diesel-based economy. But they're not without their disadvantages. To create the hydrogen in the first place, it requires the processing of fossil fuel in many cases. Toxic materials can be used to make the fuel cell, so it's not a completely clean process making the fuel cell in the first place. Like anything, a fuel cell will have a limited lifespan. It will wear out eventually, and then another one has to be made to replace it. And hydrogen itself is explosive, so obviously dangerous to store and transport. So obviously we have to start thinking about solutions to some of these disadvantages, because we want to try and have the advantages without the disadvantages if possible. So a lot of research is going into methanol or ethanol fuel cells as opposed to hydrogen-based fuel cells. These are completely independent of fossil fuels because plant matter can be grown specially for this purpose. Because this plant matter can then be fermented to produce ethanol. Secondly, methanol and ethanol are not as flammable or explosive as hydrogen, so dangers involved in transport and storage are largely overcome. There's even certain advantages in the way we could possibly store hydrogen. It could be absorbed onto a solid matrix, which renders it less likely to evaporate off and pose a fire hazard. But we still need to work on the durability of these adsorbers before they become a feasible alternative to actually storing hydrogen under pressure like it's on at the moment. So this is another electrical potentials type question, but you might spot that there's some hydrogen-based half cells in the actual table. And it says an electrochemical cell was set up based on systems 1 and 2. So again what we've got to do is work out which one has turned into an oxidation and which one has turned into a reduction. So system 1 is going to be reversed and become an oxidation, and system 2 is going to remain as a reduction. Then they want us to determine the potential of this cell, so we need to move the page down a bit to make room for that. And that gives us plus 0.18 volts. Let's go over the page and look at the next question. This is obviously a question about fuel cells, and they've got some standard electrical potentials again, a set of data. This time it's system 3 and 4. It's the same data as we had in the previous question. So I put down the two half equations. I reversed the one that's less positive, system 3. I've also had to double it because there's 4 electrons in the other one. And that gives us the overall equation written in blue. So moving the page down, let's have a look at some of the advantages and disadvantages of using fuel cells for energy rather than using fossil fuels, what we looked at a little bit earlier. So trying to stick to the main advantages and disadvantages, on the plus side you've got greater efficiency compared to petrol engines or diesel engines and the fact that pollutants aren't released. The disadvantages are that hydrogen is difficult to store and transport, and that the fuel cells themselves have limited life cycles. So let's now have a look at the answers to some of these questions and see how we did. So we got the first 3. We doubled and reversed system 4. Sorry, we doubled system 2 and reversed system 4. That was our working, and we got that second mark there. For our advantages, it's non-polluting because it only forms water, it's more efficient than petrol or diesel engines, it's hard to store, and there's a limited life cycle. So that brings us to the end of this clip on fuel cells. Thanks for listening and thanks for your time. If you've got any questions, jot them down and bring them into your teacher, or maybe have a chat to one of us at Subject Extension. In the meantime, thanks a lot and see you soon.